Okay, it is time now, 5 minutes past the hour, and we are ready to start. The first, not only first, but it is the plenary talk that is scheduled for this time, and it is going to be given by Professor Simon Levin on collective motion, collective decision making, and collective action. Professor Levin.
Yes, thank you very much. It's a pleasure to be here. And before I start, I want to just acknowledge the various funding sources that have contributed to this. I won't take you through them. So from microbial systems all the way up to socio-economic systems, we see macroscopic patterns like these bird flocks emerging from microscopic interactions. Individuals responding to their neighbors. These are all starlings except for that one hawk that's driving this behavior. And this raises a number of problems. It inescapably leads to conflicts between levels and to public goods problems. One that's very familiar to us are tumor cells, which proliferate for their own short-term benefit, but ultimately at the cost to their host organism. And we wonder whether we, as humanity, are doing this to our own planet. Public goods problems, in fact, are widespread in socioeconomic and biological context, from the sort of sharing of resources on the left to the termite mounds on the right, in which individuals engage in actions which affect the collective good. That makes them what we call complex adaptive systems. Ecosystems are, the biosphere is, heterogeneous collections of individual agents that are interacting with each other locally and evolve, and I don't mean just in a hereditary sense, based on the outcomes of those interactions. Emergent properties can include sudden phase transitions, like Martin Scheffer has talked about in his excellent book of a few years ago. Stock markets crash, the most famous being in 1929, but we've experienced the not as dramatic but similar crash in 2008, 2009. My late colleague Bob May and I, together with George Sugihara, wrote a paper in Nature just before the financial crash of 2008, in which we compared ecological systems to financial systems, to banking systems. And we said, as ecologists, we look at banking systems and we see an overconnected system that is ripe for collapse. Who knows, we wrote, how the present concern over subprime loans will pan out. Now, this was 6 months before the crisis. And of course, we know what happens. And it happened because of the emergence of macroscopic patterns, in this case, crashes, as a result of an overconnectedness of the system, the loss of robustness due to the loss of modularity. So there's been a lot of recent attention to critical transitions and to early warning signals. Martin Scheffer has been a leader in this, but ranging all the way from signals about climate systems to the sorts of tests that your doctor will do for you. My doctor does an electrocardiogram on me every year just to try to detect early warning indicators of problems. What are the challenges of managing systems of this sort? They're great. First of all, dynamics are playing out on multiple scales of space, of time, and of organizational complexity. That means that these systems self-organize. There may be multiple stable states. There may be chaotic behaviors. But that leads to consequent unpredictability, at least on some scales. The potential for getting locked into a basin of attraction from which there is no easy escape. There are multiple stable states. That means there's path dependence and hysteresis. The pathway by which you get from A to B may not be the same as you can take to get from B back to A. There's the potential, as we saw in the financial system, for contagious spread and for systemic risk. And this may be due to exogenous factors, or it may be simply due to slow timescale evolution within the system that changes the stability landscape and creates a potential for destabilization, perhaps triggered by some external event, and regime shifts. But in addition to these factors, they're the ones I'm going to focus on today, which is that there are conflicts between levels, between the interests of the agents and the interests of the collectives. So-called public goods problems, or which includes, from this lecture, things that are technically what are called common pool resources. The difference is, in a common pool resource like a fishery, if I extract something from the system, it's no longer available to you, as compared, for example, to clean air, in which we can all enjoy it without diminishing the ability of others to enjoy it. This leads to interest in how do we achieve cooperation, and to the focus of my lecture, collective decision-making. How can we achieve better outcomes for societies while incentivizing individual agents to act in the collective good? Now, problems of public goods and common pool resources are obviously central to our future, yet we are eroding them. I've just chosen one here from E.O. Wilson's book showing the rapidly expanding extinction rate of a wide variety of species, but we're also polluting the atmosphere and as we all know, increasing temperature and changing climate and physical factors in other ways. Why? Well, because we discount the future, and we discount the interests of others. We're not yet at the stage where talking on cell phones on international flights is permissible, but you can imagine what the problems would be and how uncomfortable it would be if we ever got to that stage. We live in a global commons in which individual agents are acting largely at their own self-interest and not taking into account the social costs of their actions. And the problem from a game theoretic point of view are free riders, individuals who are riding along, getting the benefits of the system without paying their own fair share. The idea of the commons was introduced 2 centuries ago by William Forster Lloyd when he introduced the notion as a place which was a shared grazing ground and perhaps multiple use system. But it was left until about 60 years ago for Garrett Hardin to rediscover Lloyd, and talked about what he called the tragedy of the commons. And he meant the tragedy of the unregulated commons, how this selfish behavior on our own part was likely to lead to the collapse of things that we needed. The solution for him was what he called mutual coercion, mutually agreed upon. For Hardin, this largely meant a role for government, a top-down approach to modifying individual behaviors. But my late colleague, Lynn Ostrom, working with small fisher societies, showed that cooperation in those societies could arise from the bottom up due to mutually agreed upon and shared norms. These sorts of problems, public goods problems, I should mention, represent central challenges not only in social and economic systems, but also in evolutionary biology, where we talk about the tragedy of the commons and the public goods dilemma. For example, organisms produce many public goods. Information is the most obvious one, and those bird flocks, they are sharing information. I'll come back to that. I showed you the termite mounds and other sorts of structures like nests that are shared and are in the collective good. Organisms in the ocean will produce siderophores that help us to chelate essential nutrients, essential elements that can then be available later. However, if an organism chelates iron, that is out there and available to everybody. Plants fix nitrogen, drop their leaves. Those leaves could be available to their free-riding neighbors. Plants produce antibiotics, and of course we have our own problem with antibiotics in society as a public good problem in terms of the overuse. Vaccines, not on this list. There's another example where the collective good becomes an important aspect of whether individuals should become vaccinated. And bacteria produce extracellular polymers that provide a matrix for growth and a signal for quorum sensing to help them create the biofilms that are so important to their spread. So bacteria cooperate and they signal each other by the production of public goods. Now, what about human societies? Well, in human societies, we have a variety of mechanisms to deal with these public goods problems. Insurance agreements, perhaps the most familiar, they spread the risks, basically creating a public good or a common pool resource. Let me give you an example of this. This is work with Avinash Dixit, the economist, and Dan Rubenstein, the ecologist. In East Africa, where Rubenstein works, herdsmen share grazing grounds. And this is a well-established principle. But the question is, why should one herdsman share his grazing ground with a neighbor? For example, if I'm having a bad year in terms of climate, my cattle are not doing well, I'm going to go to Panos and say, Panos, can I send my cattle over to graze on your land? And he said, well, that's going to cost me. Why should I let you do that? And my answer is, well, because next year the situation might be reversed. Make the calculation. We'll have a deal. So he makes that calculation. But let's suppose, first of all, someone's in charge of the whole system, owns my ranch, owns Panos's ranch, takes into account that each of our ranches, let's say independently, can have good years, in which case there's a yield of A sub H, or bad years, A sub L, and looks at what the total yield is in the system. And then says, suppose that Panos is having a good year and I'm having a bad year. The person who's in charge is going to move a certain number of cattle from my land to his and let them graze on his land. Let's say that number is M. Each of us is making investments in our cattle and in our land. So the first question is, what would be the social optimum? And to compute the social optimum, Avinash and Dan and I looked at the following function. It could be modified slightly. For those of you who are economists, you'll recognize the Cobb-Douglas sort of payoff function, x to the alpha, z to the beta. X, remember, is my investment, in this case, in my cattle, and z in the land. And so the idea is we have 2 years, A1 and A2, those are the payoffs. And so the payoff on Panos's land will be his yield, A1 times X1, the number of cattle he had, plus M, the number moved over from me, raised to the alpha, Z1 to the beta. And there's a similar term for my land, and then a cost function. And so the social optimum would involve maximizing this function over X and Z. But can the social optimum be achieved? And if whoever was in charge of these systems then turn things over to us, Panos would have to make the calculation and decide what his own payoff would be. And that would depend on the discount rate. He would be likely to let me send my cattle to him if his discount rate were not too high, but if all he cared about was this year, he would say no. But suppose that it's not a Nash equilibrium, then one looks for what's called a second best solution. In other words, Panos says to me, I can't take all of your cattle, but you can send me 10 cows. And I know that that means that next year I can only send you 10. So this system, this 3-step system, and maybe a 4-step system that I'll mention in a moment, applies to almost any agreement in dealing with public goods. First of all, figuring out what would be best for the collective. Secondly, asking, how do we get there? Can we get there simply by a bipartisan sort of agreement? Is there a Nash equilibrium? And if not, is there a second best solution? And we see this appearing over and over again. The fourth point that I said might come in is the fact that Panos might be a friend of mine. My daughter might have married his son, and he says, well, it wouldn't be a good agreement for me alone, but because I care about you, prosociality can enter into this formula. And caring for others and caring for other countries is something that's much harder to get into the equation, but plays an important part. Now, why should prosociality even be there? Why do we care about others, especially others that are not related to us? This is a problem which has been examined by a variety of people. Herb Gintis, one of the first to write on solving the puzzle of prosociality. Why do people do anything in the collective good? And if we had time, I'd give you lots of examples of prosociality, which also includes, by the way, spite, in other words, punishing other individuals who are engaging in antisocial behavior. I'll come back to that. My former postdoc, Errol Akçay, led a paper on this. And with Avinash Dixit, I published a paper which shows how prosociality arises. Without going into the math, let me explain. I've already shown, we already know that in a prosocial world, everybody is better off. So I want my children to live in a prosocial world, and the model we looked at says, suppose I can invest in education to try to create more prosocial behavior for my children. Will I be inclined to do that? And we show that this will work. And it's one of the reasons that prosociality arises. More generally, Ernst Fehr has been the leader in showing how social norms can sustain and enhance prosocial behavior. In a gathering of this sort, what he would do would give everybody a certain regimen of resources that they could either use for themselves, they could contribute to a public good, or they could use it to punish other individuals. And he plays this game repeatedly, and everybody knows who gave and who didn't. Initially, people are somewhat selfish, keep a lot for themselves, but over time, they begin to punish other individuals who are not contributing to the public good. And individuals, therefore, for fear of being punished, will contribute more to the public good. And a gradually, prosocial behavior arises and spreads, and so does the willingness to punish other individuals. So we learn that humans will punish others who deviate from social norms, even at cost to themselves. There are various games that I play with my class that demonstrate this. Punishment itself becomes a norm, which can evolve from these repeated interactions. These norms are really important to understand much prosocial behavior, and a lot of our work is trying to understand how social norms arise, how they're sustained, and how they can be suddenly changed. For example, attitudes towards smoking in public places, foot binding in China, and others. Eventually, over time, these norms may become formalized into rules and laws in society. Thou shalt not kill, thou shalt not steal, for example. One example of this, in which we built on Lynn Ostrom's ideas with Alessandro Tavoni and Maya Schluter, is thinking about individuals withdrawing from a common pool resource like a fishery. The idea is if I own that area alone, if I were the only one who was able to withdraw from that, I would worry about the future. I would, depending on my discount rate, I wouldn't take everything out at the highest rate. But if it's an open access fishery, if I leave it there, you're going to take it. And so the system, as has been demonstrated in the theory of bioeconomics, will be overexploited. So how can we get around that? Well, suppose some subset of us care about preserving for the future, and we get together and we say, we're all going to withdraw at a lower rate. But what about those individuals who don't agree? We'll have to punish them in some way. We'll have to ostracize them. So this was the idea that Lynn Ostrom put forward. And here we have cooperators, these C individuals and defectors, and these are their utility functions. The cooperators have a utility function that depends upon their own effort level, which is the amount they're going to withdraw, and the resource level. The defectors are withdrawing at a higher rate. This E sub D is higher. The resource level is the same. So this is going to be a larger term than this, but then they're going to be punished. And the punishment is going to depend upon how selfish they are. And this term here, which is the ostracism function, which depends on F sub C, the fraction of cooperators. This set of equations has to be complemented with equation for the resource level, which also changes in response to what's being withdrawn from the system. So something interesting occurs when we examine this. First of all, in the model itself, individuals that withdraw more, we compute what the social optimum is, and individuals who withdraw more than that are ostracized. This is the system of equation we look at, where f of c this is what's called the replicator equation. It really just arises from looking at the rates of change of the cooperators and the defectors and finding how the frequency changes. And this pair of equations defines the dynamics of the system. And this is what we find. We find that there's a threshold level of cooperators such that if you're below that threshold level, the system crashes. In other words, everybody is selfish. But if you can get above it, you can move to a cooperative equilibrium, which is much better for society. It's not the social optimum, but it's better than everybody for themselves. And this sort of idea underlies all international agreements. That is, in order to get them to work, you need to get the number of signatory nations above a threshold amount. If you can get it there, you can sustain some sort of cooperation. Now, we extended this, I'm not going to talk about it, together with my student, Andrew Tillman, in looking for second best solutions as well, where we say, okay, we can't achieve the social optimum. What's the best we can do? And to make the same sort of computation that we made previously. So the summary so far is collective action can be effective if it includes enforcement. Prosociality is an important contributor to the maintenance of public goods and common pool resources. Now I'd like to turn to asking, how are these collective decisions made? And I'm going to go from bird flocks and fish schools to human societies, starting again from these marvelous murmurations of the starlings, to look at the dynamics of collective phenomena and collective decision making. And I'm going to begin from work from a few years ago with my former postdoc Ian Cousin and two collaborators. We published this in Nature, and what we did is we began by developing an agent-based and individual-based model of fish, because that's the experimental animal that Ian was studying. Same ideas, however, applied to bird flocks. And this is about how animals move, but you can think about this about humans moving in some decision space, some behavior space. So every fish has its own vector describing its movement, which it updates on regular time intervals based on where it thinks the food is, where it thinks the predator is, where it thinks it ought to go, as well as what its neighbors are doing. So how do we trade off the behavior between individual decisions and collective decision making? How does social learning arise? When should social learning arise? And the way we do this is at time step, individuals update their velocity vector to be a weighted average of G, which is where they think they ought to go, and S, which is the average direction or velocities of its neighbors, with a weighting factor omega. So omega is how much attention you give information. If omega is 0, you're simply a follower. If omega is large, you pay no attention to other individuals. So I'm going to show you some simulations. And in those simulations, each individual is different. And in the first one, 99 out of 100 individuals are pure followers. The one individual is a leader, but pays some attention to the flock. So one informed individual in a group of 100. The one informed individual is the white dot, which you probably are having difficulty seeing here. It's out to the upper right because the individual would like to go here, but keeps being pulled back into the pack, which goes nowhere. But if I increase that 1 to 5, which I'm having trouble doing here. If I increase that to 5, then those 5 individuals eventually make their way to the front, and the slug moves haltingly up and to the right. If I increase that to 10 individuals, then the slug moves rather rapidly up to the front. So the first thing we see from this is that animal groups can be led by a very small number of individuals. What you're seeing here are groups of different sizes. The red line there is the largest group, but when the proportion of informed as it increases, the group moves with increased accuracy up to its goal. In fact, if instead of plotting the proportion, I plot the actual number of informed individuals on the bottom, then by the time we get to 5 or 10 individuals, the group moves very rapidly up and to the towards the goal. Think about that in our own societies, not in terms of movement, but in terms of how people are forming their political decisions. We're going through this in the United States now. A smaller number of individuals are driving a lot of followers into a polarization of the society. So I have a separate lecture on work we're doing on polarization, an increasing and dangerous tendency in our society, no matter what your political position. Now, what if, in fact, not everybody wants to go the same direction, but we have 5 individuals who want to go here and 5 here? Do we get polarization or do we get consensus? Well, if if the individuals are far from the target, then initially they split the difference in our model, but at some point that can't go on, and either the group has to move one way or the other, or it has to split apart, or it has to do something more interesting. So for example, in this simulation, 5 individuals want to go north, 5 want to go south. Eventually the group splits. But it's also possible, because our model has a stochastic element in it, that what will happen is the group will move towards one goal and then move back towards the other. Why does that happen? Well, when you get up close to this one goal, the stochastic elements tend to dominate. Not all of the vectors are pointing in the same direction, and the group is driven in the other direction. I wonder if this might not be a good model for what goes on in political parties. As political parties achieve dominance, fighting within the group becomes more important than fighting between groups. Now, we've done a lot of different modeling of it. The simplest model is called the Kuramoto model, probably familiar to you a lot of. Ignore these K terms for the moment. We have a group of individuals that are driven this is just the heading, the direction. And we have a group of individuals driven in the direction theta 1. And this is the dynamics of, those are individuals who want to go on that angle. So theta J dot equal to the sine of that, that'll drive them in that direction. We have another group that wants to go in a second direction. And we have a third group that doesn't care at all. And then we add this term here, this K term, which is a weighted average of other individuals' vectors. And if the K is very strong, will result in the group essentially achieving consensus. If K is 0, obviously you're going to get part of the group moving one direction, part of the group in the other direction, and the third group just wandering around or doing nothing. Turns out this is a gradient system. In other words, you can write the dynamics of this as the gradient of a potential, and it evolves to the minimum of the potential function. I'll show you this. This captures some of what's going on, but I just want to say that to explain all of the behavior, we needed to go to explicitly spatial models that I won't talk about today. But what was going on in that very simple Kuramoto model is that we have individuals that want to go, the red individuals want to go one direction, the blue individuals another, the black individuals just followers. And I'm sorry about that. On the fast time scale, we show that the system, mathematically the system breaks into 2 time scales. On the fast time scales, individuals are form in their own groups, the red group, the black group, the blue group. And then on the slower time scale, those groups relate to each other. What's really important is that those followers, those unopinionated or individuals, are really important to achieving consensus in these systems. So we went on some years later to look at how these ideas might extend to other animal groups and to human groups. And we showed that the uninformed individuals are really crucial to promoting consensus. They provide the potential for the big shifts in attitudes. They provide the potential for the group to hang together. So we went back to our model. We did experiments, which means Ian did experiments on his fish flocks, and we developed models for human decision making that I'll show you in just a moment. And we added another element to them. Some individuals wanted to go in direction A or had opinion A, and some individuals wanted to go in direction B. More individuals wanted to go into direction A, but those who wanted to go into direction B were more forceful in their feelings, less likely to change their opinions. And so what we looked at is the strength of the minority preference to the majority preference, how much more strongly the individuals holding the minority felt. And this is the probability in the model that I already showed you, but we also did this in the experimental situation, that one would reach the majority target, the target that most individuals wanted. If we look over here on the left, omega 2 over omega 1 equals 1, that means the minority individuals don't hold their views any more strongly than the majority views. And in that case, you're almost certain to go to the majority opinion. But as you increase the strength with which the minority holds their opinions, and just look at what's happening in the United States now, the probability of reaching the majority target diminishes until eventually, if the most stubborn individuals are in the minority, they will win out. To look at this in a different way, the number of uninformed individuals on the bottom, in the previous slide, we had only individuals who wanted to go direction 1, direction 2. In other words, who held opinion 1, opinion 2. But now we add some of these uninformed or unopinionated individuals, these followers, and something very interesting happens. If the number of uninformed individuals, we started with these strengths of preference. If the number of uninformed individuals is 0, well, the majority in this is likely to win out, but only slightly. If you increase the number of uninformed individuals, the number of followers, that increases the chance that the majority opinion will win out, but only up to a point. Because if you dilute the system enough, then you're going to tend back down closer to a random system, 50-50, where the few individuals who are opinionated have very little sway. Now we modified this to look at various kinds of human decision-making models, and we continue to look at these. Something called the adaptive network model, which means you start with a large network, which you initialize as a random graph, the Ernest-Renier graph. There are n nodes, and each one has degree 10, mean degree 10. Now we could modify that and look at the variation. What that means is that every node is connected to 10 other nodes. And then individuals, every individual has an opinion. Those individual opinions change. A focal individual will change its opinion with a probability that it depends on how many individuals it's connected to have opposing opinions. And we use a nonlinear function and look at various nonlinear functions to see the effects of that. There's also the possibility of just a random switch that I will change my opinion with a certain probability. I have a certain preference that's built into me. I'm more likely to switch towards my preferred opinion than away from it, but I may not. In other words, I may belong to a political party which has some opinions that aren't my natural tendencies. but I adopt those opinions, but there's a certain chance that I will switch back to my naive opinion. On a longer time scale, I may decide I don't like the individuals I'm connected to. I don't like the political party I belong to. So links are made and broken that's based on on how similar the other individuals that I'm connected to are in their attitudes. Now, going back to those bird flocks, I had a student many years ago named Danny Grunbaum who was working on krill populations. Those not birds, not fish, but krill in the ocean. And he was interested in how they navigated the resource landscape. So I've got this is actually his diagram, although he never published it. That resource landscape shows where the resource is in high abundance, where it's in low abundance. And if I'm an individual krill, the logical thing to do would be to climb up the gradient. But that might get me to this low peak here. So maybe I would be better off sharing information, following other individuals. But if everybody just chooses to follow other individuals, they'll be in just one big group that doesn't have anything to do with the resource. So from the group point of view, there's an optimal trade-off between finding my own information and following other individuals. But from an individual point of view, I don't care about what the collective optimum is unless I'm very prosocial. And so there's a game theoretic problem here. The question is, how many leaders will emerge in individual groups? How many followers? Going back to the same approach I laid out at the beginning, what would be the social optimum for the group? What's the game theoretic solution? Is there a Nash equilibrium? And if not, are there second best solutions? So how are bird flocks and fish schools and our own societies organized? There are lessons here for cooperation in public good situations. My student, Eleanor Brush, working with my colleague Naomi, Eric Leonard, and me, went back to the bird flocks. Observations on the bird flock shows that individuals typically pay attention to about 7 of their nearest neighbors. And Naomi and her group showed that actually is about the number that would make the group most robust. So in some sense, that's the social optimum. But Eleanor took another approach and said, let's look at this from a game theoretic point of view and see what should individuals do. And she found in this paper that we published together that the answer depends on the situation. It depends on whether you're trying to escape predators, as in those bird flocks, or whether you're searching for food. But the idea is that she looked at it from the bottom up, from the individual point of view. So throughout this, we're seeing conflicts between individuals and the collectives to which they belong. And the same applies when we're dealing with cooperation at the international level. How do we get cooperation in dealing with climate change and dealing with COVID-19, et cetera? Scientific consensus is strong on many core environmental issues, but we haven't taken adequate action to address them. Why? The primary limitations aren't that we don't know the science and what to do, but we can't deal with the social science and how to get people to be willing and governments to be willing to commit to the collective good and to cooperate in finding solutions that benefit everybody. Discount rates vary within individuals, across individuals. And to give you an idea of that, Marty Weitzman, the late excellent economist, took a survey of other economists as to what discount rate we should use for dealing with environmental challenges. And he found a huge variation among them in what the discount rate should be, ranging from 0, meaning we ought to value the future at the same rate as we do today, to very high discount rates. And of course, across different kinds of individuals. CEOs of companies will have very high discount rates because they have to produce on a short time scale. Politicians will have a high discount rate because they need to be reelected, and much greater than what societies will be. And across societies, there'll be big differences too, depending on where they are on the developmental spectrum. The central issue
is, Simon, can you finish in 2 minutes, please?
Oh, Okay, I will finish in two minutes. The central issues are issues of behavior and culture. I will have to leave aside the ways of dealing with these international problems, but we've been applying the same sorts of ideas to dealing with issues of climate change and other issues. So let me just go to the end here. Good thing you told me that. So I'm moving too slowly through this. So Adam Smith argued that talked about the invisible hand. He said, by pursuing his own interests, the baker frequently promotes the interests of society more effectually than when he really intends to promote it. The invisible hand does not protect society. Those lessons are magnified when we're dealing with ecological and environmental systems. Many people talk about the goddess Gaia protecting us. There is no goddess Gaia. Public goods and common pool resources represent fundamental challenges in economics and evolutionary biology. Collective action can emerge from local interactions and can impose the mutual coercion mutually agreed upon. Linking these is going to be key to understanding the management of the commons. The emergence of cooperation within our societies is often for the benefit, has been for the benefit of conflict with other groups. Understanding how to achieve international cooperation, I think, is at the core of achieving sustainability in dealing with our common enemy, environmental degradation. So I'm sorry I didn't get to talk about the international agreements, but thank you for listening to me.
Well, thank you very much, Simon. Thank you. Thank you for a very, very colorful presentation that you touched upon several aspects, several facets of real life. Since we are a little short on time, we'll take one or two quick questions, please. You can jot it down in the chat, or you can unmute yourself. Okay, here's one. Communication between animals is limited to their physiology. Among humans, every few decades, new communication technologies emerge. How do you think these changes would alter collective actions dynamics?
Well, I think that's a great question. I think we're already seeing how that's happening through social media, through the internet. Obviously, mechanisms that other animal groups don't have. I'm afraid I haven't seen it leading to I think as we say, the school is still out. We don't know the answer, but it does not seem to be leading to a more cooperative environment as we're seeing increasing populism, increasing nationalism, increasing polarization. So I think we'll know better in 10 years, but it definitely makes achieving cooperation in human societies different than in other animal groups.
Some other question?
Hello, Mr. Agirakis. I'm George Megas from Greece.
Yeah.
Can you hear me? Hello, Mr. Levin. Well, I'm amazed about the presentation. I should have been earlier here, Professor Agirakis. Well, I love physics. I love social aspects, and and biology as well. And I wondered if we could actually include lower level of analysis on such issues. Like, for example, Richard Dawkins said that it's very rare to see altruistic patterns in, for example, animals, like even Darwin studied pigeons, for example. But this can happen only if it's for the benefit of the continuousness of the genes, or smaller parts of the gene as well. And this can actually probably lead to our actions. And as you said, only if it's for some kind of benefit, we can find cooperation and altruistic patterns. Can this analysis go even deeper and include this kind of things? And who knows, even deeper, like why did macromolecules appear and actually, I don't know, membranes? It's because of to have the lowest energy in the system, and not only see it on. We saw game theory in there, we saw everything, but I was amazed. I mean, it's close to something, I don't know.
Well, let me try. Let me try and answer. I interesting question. Certainly, game theoretic approaches are being used at many of these very low levels of biological organization. We've done work on the bacterial biofilms showing how the let me call it willingness to contribute extracellular polymers can evolve and collect, and even these ideas are being applied to tumor growth and to methods for undercutting tumor growth. As we move to human societies, I think one of the things that's crucial to see is that although I have a lot of respect for Dawkins' ideas and those insights, that we can't be satisfied just with genetically based evolution. There's cultural evolution that's taking place
Of course.
as well in social behavior, and that's extremely important in understanding things. But game theoretic methods and dynamical systems more generally are playing a fundamental role in understanding how these behaviors evolve. And just as a closing point, historically, a lot of people have looked at these as optimization problems. If you look at optimization problems, you miss a lot of the detail that comes about in terms of the fact that individuals and individual cells are interacting. So it's a game theoretic problem that one has to be addressing.
Okay, there's one last quick question, and we hope for a quick answer. What do you think is the role of uncertainty in the emergence of cooperation? Can cooperation emerge when information transfer from agent to agent or agent to environment is noisy or uncertain?
I think that uncertainty is probably the most important factor in understanding much of life history evolution of organisms. In fact, it explains a lot of the uncertainty is what explains a lot of the diversity in biological systems as different genomes have found different ways to solve these problems. Cooperation often evolves in response to uncertainty, certainly insurance agreements and things of that sort of this. So I think uncertainty, not only can cooperation evolve in the face of uncertainty, it evolves often because of uncertainty. So great question.
Well, thank you very much. Remember that in half an hour, there is a coffee break. So people can continue their discussions there, but I'm afraid we have to stop here this session and proceed to the next session. Thank you very much, Simon. It was very, very colorful, very, very nice and inspiring. Thank you.
Thank you. Thank you.
Okay, can you stop sharing, please?